we need to be able to apply what we did in example 6 to a real life given situation. So here we've got someone spins a spinner 12 times and it either lands on red or it doesn't land on red. And the probability of it landing on red on each spin is 0.3. So you can think of this as we've got 12 trials and the probability of success, where success is getting a red, is 0.3. So before we do anything, we need to define a variable, a random variable. So we're going to say x is the number of reds we get when we spin the spinner 12 times. And you should recognize that this x is going to be binomially distributed because we're doing 12 trials, so it's binomial 12. And because we're counting up the number of reds, here success is getting a red. So the probability of success is 0.3. So x is going to tell us how many reds we get. Well, we want the probability that we have no more than 2 reds. So the probability of x is, we need to write this as an inequality. No more than 2 means we want 2 or less. So x can be greater than or equal to 2. If we were to kind of put these on a number line, the possible number of reds that we could get 0 reds, 1, 2, 3, 4, etc. all the way up to 12 reds on our 12 spins. Now we want the probability of x being less than or equal to 2. So that means we want to include 2 and we want to go down to 0. So we're going to use the calculator function and we want distribution, binomial, CD, cumulative, because we want to add up multiple probabilities, and we want to add up all the way from 0 up to 2. So from x equals 0 up to x equals 2. So we're going to put our lower as 0 and our upper as 2. So that's going to add together the probability of x being 0, add the probability of x being 2, add the probability of x being 1. And the number of trials is 12, and the probability of success, probability of red on each trial, is 0.3. So we get that's 0.253. And we normally round to 3 sig fig in stats. Okay, in B, we want the probability that we have at least 5 reds. So let's write that as an inequality. The probability of x being at least 5. At least 5 means we need 5 or more, so x is greater than or equal to 5. So if we draw out a little number line again, for these are my possible x values, all the way up to 12, because we can't have more than 12 reds, because we're only spinning the spinner 12 times. Now we want x is greater than or equal to 5, so we want to include 5 and go all the way up to 12. So all we need to do is go to our calculators and change the lower to 5, because we want to include 5, and our upper as 12, and that's going to include 12. And we've still got 12 trials, and the probability of getting a red is still 0.3. So that's 0.276. Okay, in part C, she's going to use this spinner to play a game. So each person is going to spin the spinner 12 times, and the number of reds is going to determine whether they win a prize or not. So in order to win a prize, they need a certain number of reds, and if they get more than the kind of minimum number of reds, then they'll still win the prize. So for example, someone who spins 12 reds is definitely going to win the prize. So we need to work out what this minimum number of reds is. And she says that she wants the probability of winning a game, the prize, to be less than 5%, less than 0.05. Now, we're going to assume, it's not a very well worded question, but we're going to assume that she wants the probability to be as close to 5%, as close to 0.05, but no more than 5%. So let's just do a bit of trial and error here, and let's just try and guess. So let's say that we wanted, let's say that you needed to win 9 prizes or spin 9 reds or more. So that would be the people that would win this game are the people that had 9 or more reds. So what's the probability of 9 or more reds? We need to include the people who get more than 9, because if the minimum amount of reds you need to win the game is 9, then people who spin 10, 11 or 12 reds are still going to win the game. So let's look at that probability. We're going to just change our lower to 9 and our upper as 12, and that gives quite a small probability, so 0.00169. So the target that they need to win the game being 9 isn't low enough. If we make the target a bit lower, then that's basically saying that we're going to make the game easier to win, and the probability of winning is going to go up. So let's say that we want the probability of x being greater or equal to 8. So this means you need 8 or more to win. Let's see what that probability is. So we're just going to change our lower to 8. And that's still a small probability, 0.00949. So that's still too small. We want to try and get it a bit closer to 5%. So we're going to make the game a little bit easier to win again, and we're going to say that you actually only need 7 reds to win. So we're just going to change our lower to 7. So you could have 7 all the way up to 12 reds and win the game, and that probability is 0.0386. Okay, so that's looking a lot better. That's a lot closer to 0.05. What we should check is can we make the game even easier to win and say that you only need 6 or more to win. So let's check what that probability is of getting 6 reds. And that probability is 0.118. And this here it's just too big. Too many people would win the game. So we're going to have to say that 7 is the number of reds needed to win the game. So let's conclude in context. 7 reds or more should be needed to win the game. Now, let's have a look at what this would look like graphically. So I've drawn a sketch of the binomial distribution 12, 0.3. So along the horizontal axis, I've got the number of reds all the way from 0 reds up to 12 reds. And the height of each bar represents a probability of getting that certain number of reds. So what we've basically found out is we basically tried 9, 10, 11 or 12, and the probability in that region was just too small. So we said, let's make the game a bit easier and say that you could win by getting 8 or more reds, and that probability was still too small. So then we included the 7 bar and said you need 7 or more reds to win, and that was close to 5%. And then we checked and what would happen if you only needed 6 or more reds to win, and we said this probability was just too big if you add up these bars. So we concluded that you needed to be in this region to have a probability, and we found that was 0.0386. The probability, if you add up these bars here, the probability of being in this region on our diagram.